All right, so this kind of speaks for itself. This is one of the problems where obviously the top block is going to accelerate to the left, and bottom block will accelerate to the right. And so now we need to look at the free body diagram. There's lots of friction forces, so don't miss them. Okay, so interacting object diagram, I wouldn't bother because I don't think it's very helpful. Oh, okay, yeah, that's right. Because there's another example similar to where it's not on a pulley and it's the 1 kilogram is connected to the wall instead of the pulley. So how does the pulley affect it? So draw free body diagrams in the same way that you would expect to draw them. So X and Y for block 1, and then X and Y for block 2. Okay. I think starting with block 1 is probably the best bet. So let's do M1 first. So we have M1G down. Okay, and then we have an M1, but who is exerting the normal force? This is N of 2 on 1. And so that's going to activate Newton's third law. So we're going to have one first law or third law pair. We're going to have an N1 down. This would be N of 1 on 2. I mean, in addition to your M2G right there. So that's the first action-reaction pair. And then the next, so what else is happening in the x-axis for 1? We've got tension to the left. Looks like it's probably bigger. Yeah, it's a big tension to the left. And then that's going to leave a friction to the right. But again, who's doing the frictioning? Okay, this is a friction force of 2 on 1, so you're going to bring that one down. This is another action-reaction pair. F of small f of k. And then don't forget F net for this one. So this is F net 1. That's pretty good for the first one. The second one, well, we've already established the two interacting forces between the objects in the system. So now it's just the rest of them, which we have that big 20 Newton. We have the big 20 Newton pull or P or whatever you want to call it, P. And then a backwards tension, which also is equal and opposite. So backwards tension. And then finally a big normal force, not finally a big normal force, but a big normal force, which gives us a third friction, running out of room. So we have 3, okay, so sorry, that's not very clear. Question.
If there's a friction on the top one and it's going to the right, wouldn't that also have the same friction on the bottom one?
Okay, so the question was if the friction's on the right, should it be the same for the bottom one? So this one's obviously moving that way. So this one has a backwards friction force. Newton's third law requires that if block 2 is pushing backwards on 1, then block 1 has to be pushing forward on 2.
Yeah, but sure there would be one on the ground as well.
Yeah, that's I wrote capital FK. So the drawing doesn't look very good, but there's 3 forces to the left on block 2. There's 2 forces down, and then 1 up and 1 to the right. And all that should add to F net on 2. If I had thought this through a little bit, I would have made the particle a little bit bigger. I would have drawn it something like this. I'll erase this in a minute, but you got to have a big particle. So you got tension, a big friction force, small friction force, And that friction force corresponds to the small normal force, right? And gravity down, M2G. And that big friction force goes along with the big normal force and then looks like a porcupine. This is what I would like it to look like. It goes a little bit more cleaner. We have 7 forces acting on block 2.
Quick question.
Yeah, question.
Okay, so the gravity of block 1, or the 1 kilogram block, is the normal force on block 2, the downward normal.
I wouldn't say it like that. I mean, the question was, so the gravity on block 1 is the normal force for block 2. Really the way you want to think about it is that gravity on block 1 is gravity on block 1. And block 2 reacts by pushing upwards on 1 with the normal force. So the normal force of 2 on 1, that is the reaction pair.
Oh, so that normal force going up is the same as the normal force going down.
Between these two.
Yeah.
So 2 pushes up on 1, 1 pushes down on 2. And if I wanted to make that more clear, I would draw the Earth, right? The Earth in the system would have, what would that have? I mean, it would have up gravity on 2 and an up gravity from 1. So the Earth in the system would have mg of 1 on Earth and then mg of 2 on Earth. So this gravity from block 1, that's the reaction pair. And this is common when we're doing these problems, is to think that these are kind of reaction pairs. These two are the reaction pairs, right?
So N21 and N12.
And opposite, exactly. Okay. Questions on online before we move on? I certainly don't mind doing this more complicated example. You guys can watch the YouTube video for chapter 8. So let's sum the forces then. I think we'll have enough room here. I can pretty much do it from memory, but let's sum the forces. So we've got 1x, 1y, 2x, and 2y. Okay. It's easiest to start at the top and work your way down. 1y. So 1y is going to be, now I have little n and capital N. I think that's probably the best. So 1y is, now let's see, it's little n minus m1g equals 0. That's the easy one. And then, because figuring out the friction forces in this example can be a little tricky. So in 1x, we've got, I'd say minus T, because tension's to the left, plus friction, which is mu little n, that's going to equal minus m1 times a. Yeah. Acceleration constraint, if you really wanted to, would be a2x. If that's positive, that's a2x equals minus a1x. And so maybe define this as a. There's no in the y direction. X direction for 2, that's probably the hardest, so let's leave that for last. So 2y, we've got, as is the case when we've got blocks stacked on top of each other, capital N minus little n minus m2g equals 0. And then finally, 2x, we've got plus 20, so the push, minus tension. That's also, there was an example where we had plus t in one equation and minus t in the other equation. Well, that's not the case here. They're both pointed to the left, so they're both minus. So it's t minus the little friction, which is mu times the little normal, minus the big friction, which is mu times the big normal. And that equals plus m2a. So as you're rewatching this recording, I mean, I would probably like pause it and reflect on all these little symbols and verify for yourself that you agree with everything that's on here. Questions, comments on any part of those sums? It's very detailed, very specific, and very hard. Probably the hardest, most detailed level of problems we'll get to in the class, actually. Certainly this semester. So yeah, finding the acceleration now, you have to kind of go through and spend some time carefully canceling stuff out. You might just add the 1x and 1y. No, you can't do that. Subtract them. I might subtract, I'm looking at it real quick. Just if you recognize that f of k equals mu times m1g, and big F of k equals mu m1 plus m2g, because they have the same coefficients. And if you shove that in, then you should be able to, subtract the equations. What I would do is I would subtract 2x minus 1x. Let's get rid of the little earth here. So yeah, I would take 2x minus 1x with these two friction equations in tow, and not like algebra sense. I mean, like I'm taking the third equation and subtracting it from the first equation. Yeah. I'm trying to do it in my head because, okay. So this would be.
So the t's would cancel out.
Yeah, so we have P, yeah, right. T's cancel out. That's the point. P, really, it's just, I mean, if you really wanted to, you could rewrite all this stuff out. Minus F. The F's actually. That's the tricky part of it.
No, that's not added on the left side. The n subtracts.
P minus little f minus big F K. I have to
subtract the
minus a minus FK, right? Oh, minus plus FK. So they do they add together in the sense that there's two minuses. This is the behavior that I would expect, actually.
Oh, is that use of n the same thing as negative f little k? Okay.
Yeah.
That makes more sense.
I guess I didn't do so. So you have to be careful with the numbers here, because little f is mu times little mg, big F is mu times the sum of them. And so I'm just going to write out something, because can you guys see over the monitors here? Okay. I'm going to go out on a limb and say it's equal to this. P equals mu. Oh, no, not P. Get ahead of myself. Acceleration equals P minus mu three M1 plus M2. Divided by M1 plus M2 all times G. Is that what the website with the Mastering Physics answers? Okay, never mind. I think that's right, because the F's, right, because there's three factors of mu times M1G in this difference. You got P minus big F minus big FK minus FK again equals M1 plus M2A. So whatever that is, 20 minus, I mean, everyone's got a different coefficient, unfortunately. If it's 0.2, it would be, let's see, 3 plus 2 is 5, so that's 1. 20 minus 1 is 19 divided by 3 over g, or whatever that is. 2. All right, so not that, I mean, it's not something that you can easily do in your head, unfortunately. If it was 0.35 for the person that asked, then it'd be like, the point is that you got 3 times 1 plus 2 in that parentheses, so that makes 5. There's a 3 down in the parentheses, or 3 down in the denominator. So you have 20 minus 0.2 times 5 is 1, so that'd be 19. 19 thirds g, which would be the answer in the book. But yeah, so that's typically how these problems go. Does that help for this example? Were there specific parts that were confusing about it? Okay, and if nothing else, we can certainly post this and look at this example. Again. So I'll make sure it's posted today, so we can look at it.
I think when you do the things over there, the different forces going everywhere that you recommend a lot, I think that really helps bring it down a lot.
Yeah, drawing the free body diagram. And this is really an example where drawing the free body, without the free body diagram, it's too easy to miss something. It's too easy to miss a friction force. And so I'm fully aware that I'm not like accepting like free body diagrams from you to be submitted for grades, but at the same time, problems like this, it's critical that you draw these things. That's why I've been drawing them, for each example that I've been doing. Good.
I did have one question. Where'd you get the 3m1 on the final equation?
Oh, that was, let me just, I guess I've already started erasing it, so let me just write it again. I did a lot of algebra at once. See if we believe it. See if what I feel like I did was right. Because 1x, you have, let's just go through it, it's fine. For 1x, we have minus t plus fk equals, minus m1a, right? And then 2x was p minus, oh no, plus. Yeah, plus p minus t minus big fk minus little fk equals plus m2a. So the question was, how did I get the 3? I subtracted these two equations, and so I got this thing minus this thing. So we got to just rewrite it. The more work you do, the better, so you don't mess it up. Minus t plus fk, and hopefully we can all agree that m2a minus m1a is m1 or m2, the sum of them times a. So the t's cancel. So it's p minus t minus little minus big plus t minus little, and so the left part turns into p minus 2fk minus big fk equals sum of the masses times a. And then I break open the friction forces and say what they're really equal to. That's equal to p minus 2 mu m1g, right? And then big fk, that's minus mu m1 plus m2g. And so you see there's, if you take the mu and distribute it into the parentheses, you get p minus 2 mu m1g minus mu m1g minus m2 mu m2g, and so that's where you get the 3. Does that make sense where the 3 comes from? You just got to work through it again. Good. Yeah, so that's where the 3 comes from. So it's kind of weird that the friction forces almost, even though they're like action-reaction pairs, they almost work with each other to make the resulting acceleration more. Yeah, because you were subtracting this in a sense. You could even try it vectorially. I don't recommend it, but you could even subtract it vectorially. That would be hard. Okay, anything else on this problem? Very good example. This is one that I would historically give on my finals. Probably not the calculation part, but certainly the free body diagram and summing the forces part, because you can, as we can see, it's certainly helpful when doing the real calculations. So if nothing else on that, any other homework questions? I'm certainly willing to take more if people want. Almost 10. Okay, well, if nothing else, then a couple remarks about chapter 8 before we do some examples. The important part is that a particle moving in a circle, got some velocity v that's tangent. We established in chapter 4 that this xy coordinate system won't really help us, but we established that if it's moving in a circle, then it has to be accelerating towards the center. Right? Chapter 4 went through kind of the vector addition and subtraction that lends itself to that central acceleration. And chapter 4 also went through a derivation of what that expression is, and that acceleration was equal to v squared over r. Right, because we're in circular motion, the radius isn't changing, we don't deal with elliptical motion. The chapter on gravity is a little bit about elliptical orbits, but they use different tools in this anyway. So basically the idea is that we introduce this Rtz coordinate system to kind of follow along the particle as it makes its circular path. So we have this, so let's see, it's a very non-typical coordinate system, but if it works, it works. So we got an r-axis that points towards the center, a t-axis that points along the direction of motion, and a z-axis that points to a perpendicular for what that's worth, and that will actually be useful for some of the problems we do today. But the important thing is we're able to constrain the radius and we're able to constrain the velocity and the acceleration into, a single axis. So we got VT, equals, not too far. No, it's fine. VT equals omega r, and then we got a sub r equals v squared over r, which could be omega squared times r. And all the other components are 0, like the v, like the t component of acceleration and the z component of v. The other ones are all 0. And so that carries over into dynamics by saying that the F net then is now equal to ma. So now we have F net only in the r direction. That equals ma. That equals some of these standard formulas that folks might remember, mv squared over r or m omega squared r. So that's kind of the starting point for these examples. That's just kind of formalities. So questions or comments before we go on, either online or in Zoom or in person. We're all online in some sense. I'm offline more than I'd like to be, actually. All right. So, quick example.
Actually, we're just I forget what it's called, the W.
Oh, yeah, W, just as a reminder, it is Greek letter omega. Yeah, this is a common thing people need refreshers on. It's called angular velocity. Yeah, so that is the rate at which angle is being swept out as it moves in in a circle. So it's technically, I mean, if you refer back to chapter 4, you'll see it, but technically it's defined as d theta dt. I don't know how helpful that is, but it's just rate of rotation. What's the angular velocity of the Earth? It's 1 revolution per day. I mean, that's the unit that is literally the angular velocity of the Earth, or 2 pi radians per day, or whatever 2 pi radians divided by 86,400 seconds is. That's just something I memorized. Seconds in a day. So that's omega. It's just a rate of rotation related to how angles swept out. Typically, a lot of these problems, we don't use omega. It shows up more in chapter 12 and someone's later ones. Quick example on turning a corner, kind of a fun one. How quickly can you turn a corner on an intersection without skidding? Does anyone have any estimates?
Intersection?
Well, yeah, I mean, you're just, let's say,
Oh, you're turning.
yeah, you're at the left-hand turn signal or turn lane, and you're trying to figure out like how quickly you can take the turn without skidding or having your tires screech. Estimates on how much that might be? 30. Okay. Not much.
This is where you have to have some experience.
Yeah, this is like the 758. We better make the light or our kids are going to be late to school and speed. Anyway.
I know 40 you skid. I've learned that one.
Oh, you do skid at 40. Okay.
Oh, yeah, exactly. How big are your tires?
Well,
How big are
I
your
got a
tires?
small car, so
Okay. Don't mind them.
it's lower down. So I think that affects things.
So if you were to say maybe like 20 might be a lower limit, 40 might be a higher limit, let's put some estimates on this. Let's have some fun with it. So obviously, as it turns the corner,
You're skidding.
if you're turning this corner at a constant speed, let's say, okay, so let's try and figure that out. What would you estimate would be the radius of this assumed circular motion?
Well, technically,
Is there, I mean, this is where we can sort of estimate.
so how wide is the average lane?
How wide is the average car?
No, the lane is what matters because that's where the
Two-lane.
lanes are.
Is it
There's only a
2
certain
lane
number
or
of
3
lanes.
lanes? Let's say, okay, the one I'm thinking of is like 21st and Rock Road. That's like the 3 lanes, right?
Yeah.
And there's a median, so that might be altogether 15, maybe 15 meters. Is 15 meters
If there's 3 lanes and there's a median, wouldn't that just be 2 lanes?
well,
Because you're turning into that turn. I'm assuming that you're in the turn lane.
yeah, so you're in the turn lane, but I think some intersections might have like oh, I love this stuff. Let's see. So we have the line where the people turn into here, and then there's also these 2 lanes, and then there's the median, and maybe like some trees or some person asking for money, and then there's the I mean, sometimes they do that for real.
Oh, you're thinking about, okay, that's.
Something, that's what I was thinking of here.
Okay, that makes more sense.
Does that seem reasonable that 15 meters would be?
Yeah, we'll go with that.
Yeah,
We added all that extra stuff, yeah. Two lane outside.
You gotta calculate how much money you're willing to give him.
with the hot dog in the middle.
Oh. Sure.
Calculate the density of the tree.
It's like doodads when you would make like your own environments in like Roller Coaster Tycoon or something. Okay, moving on. So what's the free body diagram look like for this car while it's turning? Well, this is not a good plane to look at, the bird's eye view plane. If we look at the plane right behind it, this is not going to be a good one. So this is like, okay, it's a license plate. So we're watching it turn, R axis and Z axis. Okay, and then as we're watching it turn, it's accelerating to the left in our positive R direction. So some F net. You got your normal and your MG. As usual, and those equal But what's the force in the R direction? I mean, which one of the ones that we have to choose from, really? Or is it some new one? I don't know. I mean, I know, but
Wouldn't it be the coefficient of friction times mass or acceleration? Yeah, what's holding you in is the coefficient of friction, which is friction itself.
it's friction itself. Yeah, what's holding you in is the street is literally pushing you towards the corner. The street is pushing you towards the corner, because if it wasn't there, you meant trying to make a turn, your tires say, okay, thanks for turning, I'm still gonna go straight. Right? Because the friction is what matters. And so, yeah, so friction is what's pushing you towards, it's static friction. Yeah, it is static friction, because if you look at the tires, the car is, the book has better drawings of this than what I'm doing, but as the tire is moving that way, basically the argument is that static friction is pushing on it perpendicular to the direction of motion.
Oh, yeah.
So we have a static friction force literally pushing the car towards the corner as it's moving. So the friction force is perpendicular to the velocity now. So I guess their dot product is at 0 in this case, right? And their cross products or whatever their cross products are. So yeah, they have to be perpendicular to each other in this setup, which is not always the case. We'll see if we have time in a minute to do the bank curve problem. Yeah, we should have time. So yeah, static friction, and if you guys accept that, then let's move on to the sums of the forces and see if we get an answer that's reasonable. So how do I sum these forces? Okay, this simple free body diagram is still useful. So we got in the R direction, we have just F of static friction equals MA or MV squared over R. And then in the Z direction, N minus MG equals 0. That's it. There's really nothing in the T direction if we're assuming that the velocity is constant. If we're like starting from rest, then yeah, there'd be like a propulsion force backward, forward, and probably also a static friction force in the direction of motion too, because that's what Chapter 7 argues propulsion comes from in a car. Well, yes and no, in the sense that in this model, it'll turn out to be independent of mass. But you're right that it really does. We just need a more advanced model to really handle it. Yeah, I'll mention that in a minute as well, because the width of the tires on the road affects it too.
Does how high your center of gravity on your car affect it too?
Yeah, sure, because
That's true.
does it affect it because there's
You turn if you look over.
you can't turn if you're flipped over, right? No, these are good questions. Does the center of gravity affect this? Absolutely. I mean, and we're only doing the most simplest of models where we're modeling the car as a particle. So the particle is like this particle on the ground moving at some speed, right? And so there's no center of gravity, there's no distribution of force between the four tires, say like on the driver's side tires versus the passenger side tires. Is it front wheel drive? Is it rear wheel drive? I mean, all these extra complications that make the problem more realistic would come up in like if someone worked for Honda or something and trying to figure this out. But in seeing if we can get an estimate to our 30 or so miles per hour, we have to turn this R equation into the maximum, because this equation by itself, this equation by itself, this static friction is not necessarily equal to coefficient times normal. It's only equal to static friction coefficient times normal force when we're at the very maximum possible friction. And so if we turn this into F sub S max, that's going to equal mu sub S times N, which equal NV max squared over r. And now we can do our simple little substitution, normal equals mg, and we'll get mu sub s times mg equals m times v max squared over r. And so, yeah, you see, yeah, the masses cancel again in this model. Okay, in this model of the simplest friction force that doesn't take into account tire treads, it doesn't take into account like width of tires, doesn't take into account center of gravity, doesn't take into account, modeling the car as a, with 4 points of contact on the wheels, that it's not variable density, that, if you got something in the bed of your truck versus like someone who's just in the driver's seat, all this affects it. Okay. Well, my wife's the only one that drives, so I hope that she wouldn't. Let's see, so the mu RG. Okay, mu RG, right? So solving, canceling for n, you get multiply by r square root. Well, let's see if we get something realistic. Square root, so the static friction coefficient for rubber on concrete that's mentioned in the book is 1. Okay. R is 15. G is 9.8. Yeah, right. And then so 15 times 9.8 is 147. So square root of 147 is a little over 12, right? That's because one. Are you serious? So maybe 12.1 or so. Okay, it's 12.1 meters per second. How do you go from meters per second to miles per hour? 3 1/4, 2 1/4, right? So that ends up being about 27 miles per hour. Well, I don't know how off you really were. Maybe this problem might be 5 off of what you actually experienced. So, I mean, a very quick and easy way to find estimate for, slipping. How fast can you take one of these intersections? It's a yellow arrow, so you're rushing to get to the place, your job interview, or wherever, and you don't want to be late. And so, I wouldn't try this, but I can't speak for you in the past. So, questions, comments on this example? It's 10:13. I'm certainly willing to talk about banked curves now. Questions or comments on any of this? You'll have something similar in your homework where you have like a penny on a turntable and those types of problems. Figuring out how quickly something can move without it slipping is always kind of fun. That's kind of what they do in these examples. Oh, I was talking about a homework problem where you have like a yeah. Right. So you have like something like that, and the turntable's spinning at some rate omega, and you're asking like how far away can the penny be before it starts to slip? It's more or less the same thing as this turning a corner problem, but just with omega instead of v. I think you're given the coefficient, hopefully, in that problem. But in moving on to these, he mentioned these like museum type things where you put a penny in and it like spins inward, and that just gets faster and faster and faster as it goes. I want to kind of motivate that by talking about banked curves. 7 or 6 or so minutes. It might have to be pretty quick. Certainly can continue on Friday, but how does a banked curve change? Because the idea of a banked curve versus that turning a corner problem, you don't even need friction to turn a corner, or more realistically, turn some wider turn, because the normal force is now the thing that's providing the centripetal acceleration. If you look at, the free body diagram of, And that way, if you look at the free body diagram of this thing, it would be, we would still have R as Z, but now an mg still always comes straight down. Oh, by the way, for some examples, Z might not even be up. Normal force is now not in the Z direction. It's still perpendicular, but it's not in the Z direction. So one big thing, conceptual thing is this, and if we were all on Zoom, I'd probably do a Zoom poll. I'm not going to, but is the normal force greater than mg, less than mg, or equal to mg in this case? Does anyone in here on Zoom want to explain? Okay.
I think it's gonna be less,
Okay, why do you think less?
because of the angle that it's sitting on. Normally gravity would be pulling on it all the way, but now since it's at an angle, it's not pushing as hard onto that as it is.
Okay, so you think, I mean, that simple like
Surface.
table on a, box on a table problem, it'll just be, or just like the homework example that we did, you got normal up, mg down, and everything's fine, right? F net is 0. So they would be equal in this case, but you're saying like on inclines that we did, like some of the problems that we did yesterday, if we got the block sliding down the incline, well then take a look. If it's sliding down the incline, you got mg down. So placement of where I label this stuff is oftentimes important. If you look at mg, part of that mg is the thing that's causing the acceleration. So you have two components of mg, one lateral to the incline, and then one perpendicular. So the perpendicular one is less than mg. The normal force here is less than mg because the other part of mg has to provide the acceleration. That's in the case of the sliding down the incline. And in fact, it's mg cosine theta. But now that we're on an incline, or now that we're not sliding down the incline, what, on this free body diagram, what's the direction of F net?
Is it in the direction of the normal force?
No. If you look at the picture, it's meant to be like,
Oh, wait, the normal force is the arrow that's looking upwards.
yeah, sorry, this is the normal force, right?
Okay, so it's more towards R.
It's actually in the R direction. All right, so we got F net in that direction. But F net is perpendicular to mg. So what can you say about the components of M? Well,
Wait, so wouldn't that make it where it has to be bigger than
it would, because now the Z component of N has to equal mg. Since the Z component of N has to equal mg, the R component has to be the thing that lets us move in a circle, right? And so we're not accelerating in the Z axis, we're accelerating in the R axis.
So F net just equals the normal force?
Well, it would, this F net would equal the R component of the normal force.
Oh, yeah, not just
And the Z component, right, would equal mg. So in that way, we observe that the normal force is greater than mg in this case. Think about the last time you've been on a roller coaster and you're like, not like at the, well, either way, I mean, just gone to the top and now you're falling down and it just, well, that's not a great example, but let's say you go down, now you're at high speed, right? And then what happens? It just turns on you, right? What happens to you when you're turning? Don't you feel shoved down into your seat? It feels like something is literally taking your shoulders and just pushing down as hard as it can, right? Well, you're being shoved down because the normal force is so much bigger now than your mg. It's not. that relative, otherwise people would get hurt, but it's still big enough to where they can take that curve pretty quickly on a small enough radius. You can feel that sensation of being shoved down into your seat. So as we're getting ready to kind of end for today, I think the big takeaway, and we'll continue this on Friday, is that normal force has to be bigger than gravity. And there's no need for friction in order to maintain a circular path. And yeah, really quickly about that, those like penny races, that's what my kids call them. They call it penny race. You have they're moving in a circle, right? And the penny's like, just going, or quarter, whatever. So it's got a specific radius and it's got a specific velocity, and the velocity is attached to a specific radius, but there's still no need for friction here. It's inertia's, it's not inertia. There's some normal force that's kind of up at an angle that is allowing it to maintain that circular trajectory while still having gravity point down. So we'll talk about this one next time, in addition to doing the bank curves, and talk about how the curves are, how big of a radius and how big of a banking angle you need if you say you wanted to design a highway at 70 some miles an hour. Okay, so any questions on Zoom from anybody? Okay, well, if nothing else, then thanks for your time. We'll all meet back on Friday then at our normal Zoom, and then we'll continue. Yeah, we'll continue, and then definitely plan for next Wednesday as a certain in-person session as well.